So, in today's lecture, I would try to do something different from what I was doing. I was mainly doing some algorithmic aspect of computational geometry, but today I will introduce some geometry graph classes or graph classes which are inspired from the geometry underneath. Also, I briefly let you know what is the approximation algorithm is, and I will present one of the geometry approximation algorithms. So, but both the topics about the problems that I am going to consider today are fairly easy, but still if you have any doubts during the lecture, please feel free to interrupt. So, the geometry graph class that we will cover today is called the unit disk graph. What is a unit disk graph? So, in a unit disk graph, you are usually given a set of unit disk in the plane. Unit disk means the radius or the diameter of the disk is 1, and you are given a set of unit disks in the plane, and from those unit disks you create a graph as follows. In the graph, the vertices are the unit disk that is given to you, and there will be or the centers of the unit disk that is given, that those are the vertices, and there will be an edge between two unit disks if the distance between any two center is less than equals to 1, or in other words if they intersect. Centers of this unit disk are the vertices, and there is a edge between two unit disks if they intersect. So, for example, you have a question? Distance is less than equals to 1, then there will be I am assuming the radius is 0.5, radius is half, diameter is 1, that is what I am using as a unit disk, that is my definition of a unit disk. So, it varies from there are two versions of unit disk where the radius is 1, where the radius is 0.5, but you can change it accordingly. More or less the point is radius of each disk is same, and there is edge between two disks if they intersect. So, for example, for the given set of disks, this is the unit disk graph that you will get. Clear?
Can the disk intersect covering the overlapping the center of another set?
Yes, of course.
So then
if they intersect, can they contain each other? I am assuming that no two centers are same. So, they cannot contain each other because the radius of each disk is same, right. But now it does not matter how they intersect, if they intersect there will be an edge.
If that one intersect, these intersect, there can be an edge between two vertices.
Yes.
Center, but see that one.
Okay.
They also intersect, but yeah, that one and just below.
Yes.
Yeah.
Let me know the number.
See, the disk with center 2 and 8, they also intersect.
Sorry, my bad. This is supposed to be the unit disk. Good observation. Okay. Definition of the unit disk graph is clear. So, we will try to ask the same algorithmic questions that we usually ask about any graph class. Is the first such question is how to find a maximum clique in a unit disk graph. What is a clique? Clique is a subset of vertices such that the graph induced by those subsets forms a complete graph. For example, 2, 3, 4 forms a clique, 5, 6, 7, 8 forms a clique, but 1, 6, 2, 5 does not forms a clique because the edges 2, 6 and 1, 5 is absent from the graph. The basic graph theory. So, this is a famous graph problem, that in a given graph can you find out a maximum clique of that graph or not. This problem for general graph classes is NP hard. That means with standard complexity theoretic assumptions, most likely there is no polynomial time algorithm for clique to find the maximum clique in general graphs. But unit disk graphs or UDGs have a special kind of graph classes. Our objective is to find whether is it possible to find a maximum clique in unit disk graph in polynomial time or not. But when we talk about cliques for unit disk graph, there are two kinds of cliques that we are concerned. One is the geometric graphical cliques, the definition that I have just given you, that if there are two, you create a graph where if two disks intersect, you create a edge between them, and in this way you create a graph, and if you are looking for a maximum clique in that graph. But there is a concept of geometric clique in a unit disk graph, that is a set of circles or set of disks for which there is a common intersection point. For example, these 3 unit disks do not form a geometric clique, because they do not have a common intersection point, whereas this 3 disk forms a geometric clique because they do have a common intersection point. Okay. But in this lecture today, we will only consider how to find maximum graphical clique that we will refer as a clique for the rest of the lectures. So, we do not consider this kind of situations. I will give you a hint maybe to how to find a geometric clique as well, but mostly we will be dealing with a graphical clique for this lecture. So, what is our objective? We are given a unit disk graph and the unit disk representation, and we would like to find what is the maximum clique in this graph. Okay. So, before we begin, let us fix some of the notations. That suppose we are given a set of unit disks that are d1, d2, dn, and we are also given a set of we are also given the unit disk representation of these disks, and the centers of disks those disks are C1, C2, Cn. Okay, these are the centers. The disks are d1, d2, dn, and the centers are C1, C2, Cn. Now, our objective is to find the maximum clique, right. Now, again, as I always do, if I can't solve a problem directly, I try to simplify the problem. How I will simplify? Suppose there is a maximum clique, whether I will be able to find out it or not, that is a different question. Suppose that maximum clique is B, and some oracle told me that in that clique what are the furthest centers or furthest disk in that clique, that is given to me. So, you are given a unit disk graph, and in this unit disk graph there is a maximum clique. There can be multiple. Consider one of such maximum cliques. Some oracle has told me that among this disk which forms the clique, d1, d2 is the furthest disks in that clique. That someone told me. Given that information, can I solve this problem efficiently? Okay? So, this is my disk which are forming the clique, and D1 D2 be the furthest disk among them. Now, to get a good algorithm, what we do? We try to find out properties of this problem. What properties can we infer from the fact that D1 and D2 are the furthest disk among the disks which creates the clique? This is the furthest pair of disks. What information can we infer? Suppose what I do is, no, may not be. The point is, if I draw a disk centered at C1, what is C1? C1 is the center of D1. I draw a disk centered at C1 and passing through C2. What is C2? C2 is the center of D2. Similarly, I draw a disk centered at C2 and passing through C1 and take the intersection of these two disks. Can I say that all the points or all the centers which forms the maximum clique has to lie in this intersection? Why? Because suppose there is a center here outside, then this will be the furthest disk. These two, C1 with say Ci, will be the furthest disk, not C1, C2. As C1, C2 is the furthest pair of disk among the disk which forms the clique. So, all that is forms the clique has to be there in the intersection of these two disks. Are you with me? Please raise your hand if it is not clear. Is it okay? Okay, very nice. So, someone told me that D1, D2 are the furthest, and we found out this intersection points. Now, the next question is, there will be lot of centers from the given set of disks present in this intersection, right? Right? Can we say that all the centers of the disk which present in this intersection forms a clique? Then we are done. What I am saying is, I know the further disk. I know that all the disk which forms a maximum clique has to be inside this intersection. Let us call this intersection say I. I know that all the disk which forms the maximum cliques has to be inside the region I. But is the reverse true? If I take any disk whose center is inside I, they will form, I will take all the disks whose center is inside I, they will form a clique. What is the radius of these two disks? No, no. Distance is, the radius is 0.5. Radius of each disk is 0.5. It is yes. Okay. The radius of this is 0.5, radius 0.5. That is the definition of the unit disk that I have given. So, this is 1, at most 1, right? So, what about suppose we have a disk here and a disk center here and a center here. Does these two disks will intersect? Yes? What is the distance between these two? Greater than 1. So, if a disk is centered at this point and there is a disk centered at this point, they will not intersect. So, what we have the furthest pair of disks. I take the intersection, found a region, and within that region there are a lot of centers. Now, my new objective is to find the maximum clique among the disk whose center lies in that region. So, we came back to the same point. We have started with the maximum clique problem for all the disks, but we have now a smaller region and we would like to find the maximum clique of the disk whose center lies inside this region, because I know that all the disks which forms the maximum clique whose center will be here inside this, but its opposite is might not be true. Are you with me till now? If there is any confusion, please raise your hand.
Sir, if 2 points lie there up and down, then those 2 points will become the farthest pair. These 2 points will not be the farthest.
Even they are not farthest, still they may not intersect. Just one, say some point is say here and here, less than something. Okay, even so, my point is okay. Maybe what is the furthest pair I am looking? Am I looking for a furthest pair among all the disks given? No. This is the furthest pair among the disks which creates the clique. It is possible that this and this are both not present in the clique. So, that argument does not hold. So, I started with a clique problem for a plane. Now, we are trying to solve a clique problem for this region, that all that is centers in this region. Did we, the question is, did we gain anything from this extra information that I have to find a maximum clique among the disks whose center is here? Let us see. Okay. So, suppose this is the intersection region and there are a lot of centers as shown in the figure, and our objective is to find the maximum clique among those disks. Now, what I can do is that I can draw a line joining C1 and C2. Consider all the disks whose centers are above this line C1, C2. Can we say something about them? Because if you take any point in this region, any 2 point in this region less than 1. So, these all these disks forms a, what about all these disks here? Very good. So, I have a graph which I can decompose into 2 parts, clique 1, clique 2. Does this graph class looks familiar? May not be. What I have? Clique 1, clique 2, and there are some edges might be going from one side to the other. Have you seen something like this? Bipartite? What is a bipartite graph? I can divide it in 2 independent sets. So, this is not a bipartite graph, but very good. It's this graph is a complement of a bipartite graph. In bipartite graph, what we have? Two independent sets and some edges going between them. What I have here? Two cliques, some edges going between them. So, this is basically a complement of a bipartite graph, because if I take the complement of this graph, there will be no edges between the vertices here, there will be no edges between the vertices here, and there will be some edges going from this component to the other component. Are you still with me? Okay. Step by step. What we are looking for in the original graph? A maximum clique. If we are looking for a maximum clique in G, what we are looking for in G complement? So, everyone knows the definition of a graph, complement of a graph. If you do not know the definition of a complement of a graph, please raise your hand. Okay. It is a graph with the same vertex set, but the edges becomes non-edges. Suppose there is a edge between A and B, then there will be no edge between A and B, and the non-edges, if there is no edge between A and B, there will be edge between A B. So, non-edges become edges, edges become non-edges, vertex set remains the same. So, the question is, if we are looking for, if set of vertices forms a clique in G, what they form in G complement? Independent set, right. We started with the complement of a bipartite graph, now we move to bipartite graph. There we are looking for the maximum clique, here we are looking for a maximum independent set. But maximum independent set is usually like NP hard, and it is notoriously NP hard, even finding some approximation is very difficult. So, now what we are trying to do is trying to find a maximum independent set, but not for a general graph, but for a bipartite graph. How to find that? So, these are the small tricks that we use very often in graph algorithms that I just want you to know. So, we are looking for a maximum independent in bipartite graph. How to find a maximum independent in a bipartite graph? Anyone? Yes.
A and B.
Hmm.
So, independent vertices are typically A and B.
What? Okay. Yes. Let me. If you think about bipartite graph, it might not help. Again, think about. Let's play with some graph theory. Suppose A is a independent set in G. My question is, what is suppose A is an independent set. What is V minus A is? V is the vertex set of the graph G. Very good. Take any independent set. if you take, suppose A is any independent set, take the V minus A, that will become a vertex cover. Why?
They don't contribute anything to edges.
So, whatever rest vertices are, all the edges has to be incident upon them, because there is no edge between two vertex in A. So, all the edges what we have. So, there is no edge between, so this is an independent set, that means there is no edge between them. So, all the edges are of the form so, suppose the independent set is red and all the vertices are green. Every edge has to has at least one point in a green vertex. We cannot have a edge whose both endpoints belongs to a red vertices. That will contradict the definition of an independent set. So, these are small things that are useful to know while doing some graph algorithms. These connections are very important. Is it clear to everyone why a complement of a independent set is a vertex cover? So, what is the complement of a maximum independent set? Is a minimum vertex cover. So, again we started with our journey from a complement of a bipartite graph. What we are trying to find? Maximum clique. We move to a bipartite graph, there we are looking for a maximum independent set. What is the complement of a maximum independent set? Is a minimum vertex cover. Now, in a bipartite graph we are looking for a minimum vertex cover. It is okay? Are you with me? How to find a maximum vertex cover in a bipartite graph? That is conics theorem. There is a famous theorem that from the maximum matching in a bipartite graph you can quickly find a minimum vertex cover. This is basic graph. This is basic graph theory. See, so this is actually a paper, and this is consists of only few observations, but the key point is how they have connected the arguments one after the other. We have started with this. We started with the assumption that we know the furthest point. If we do not know, what we will do? We will guess all possible n square choices. There are n square choices for the furthest pair in the clique. I will take their intersection, I will find a region I will look at the disk centered at I, that will give me a graph, that will induces a graph which is a complement of a bipartite graph, where I am trying to find a maximum clique. I will convert this to a problem of finding a maximum independent set in a bipartite graph. That is a vertex cover, minimum vertex cover, it is a complement of a minimum vertex cover, and finding a minimum vertex cover in a bipartite graph is polynomial time solvable. Step by step, small assumptions, small observations, it leads to a something of significance. Difficult? No, right? But you have to make those connections, that is the only difficult part. Are you with me till now? All okay? I can repeat if it is not clear. So, we have started a restricted problem that we know with the assumption that we know the furthest pair among the vertices which creates a maximum clique. Some oracle told me, but suppose we do not know, what I will do? I will try all possible choices. How many choices are there? N square choices, order n square choices, right. So, n square into the time required to solve a minimum matching in a bipartite graph. That will be our complexity of finding a maximum clique in a unit disk graph.
Minimum matching between upper clique and lower clique.
No, bipartite graph you have two parts, right. So, the graph is like this. In this graph you have to find the maximum matching. So, there is no edge, this is independent set, this is 1 is independent set, 2 is independent set. So, all the edges come going left to right.
That maximum matching is the minimum vertex cover.
Yes, maximum, from maximum matching you can get a minimum vertex cover. Maximum matching is a set of edges, but when if you know the maximum matching, then you can get the minimum vertex cover very easily. That is Koenig's theorem. All good? Okay. So, I will keep this as homework, that how to find a maximum geometric clique in a UDG. But you see, what is a maximum geometric clique? It is represented by a point. If you take a set of unit disk, that will divide the plane into some regions. From that region you have to choose one of these points. You think about this, I will not go into the details of this. Okay. So, we are done with maximum clique. What about maximum independent set in unit disk graph? For a general graph, this is a notorious, like it is a very difficult problem to solve from all respects. This is, of course, it is NP hard, maximum independent set in a general graph.
So, for the previous problem, we got maximum, we got some clique in the upper half. So, between the
No, this is not the graph anymore.
no, that intersection which you are saying. Next. Yeah. There you can have a clique, and here we have a clique.
Yes.
Between the C1 and C2 above, we set up vertices. So there within the radius 1, so there you can have a clique there. And here also a clique is there.
Yes.
So
This is the graph you will get. This is the kind of graph that you will get. But if you take the complement of this graph, you will get a graph, a bipartite graph. In bipartite graph, now you are looking for an independent set. What is the maximum independent set? Is a complement of a minimum vertex cover.
then corresponding to that we will get the maximum.
And you will go now trace back your path through the original graph. Okay. Any doubts? Please let me know if there is any doubts. Okay, so our objective is to find the maximum independent set. That is a maximum number of disks which are pairwise disjoint. So, if this is my set of disks, this is one of the maximum independent set of disks, the red ones. Is it visible, the red color? But the unfortunate thing is that this problem remains NP hard even for the unit disk graphs. Unlike clique, which is polynomial time solvable for unit disk graph, but this maximum independent set problem remains NP hard for even UDGs. Yes, there can be many independent. So, if I take say this and this is independent, I can introduce this, this is this. These 4 are also independent sets. There can be many independent sets, there can be many maximum independent set. I am looking for one of them. But with standard complexity theory assumptions, most likely it is not possible to find such a maximum independent set in polynomial time. We do not know yet whether it is possible to solve this in polynomial time or not, that we do not know, but it is widely believed that it is not possible. So, what to do?
Also finding maximum independent set is also
Then notoriously difficult. Why? What do I mean by notoriously difficult? You will be clear in a moment. NP hard, this is NP hard, but there are levels of NP hardness among the problems. So, can you solve this problem in 2 to the power n time? So, there are n disks. Can you find, let me know what is the maximum independent set in time 2 to the power n? How many subsets are there? If there are n disks, how many subsets of disks are possible? 2 to the power n. You check all of them and find out if this is forms an independent set. If I give you a subset, can you let me know whether it is an independent set or not? Yes, there are 2 to the power n subsets. You check all possible subsets and see that whether either they are independent or not, choose the maximum. So, certainly it is possible to solve in 2 to the power n time, right. But my question is, can we solve this in say n to the power k time, where k is a constant? That is not known whether I can solve this problem in n to the power k time or not, whether there exists algorithm which solves maximum independent set in n to the power k time or not, but it is widely believed that it is not possible. That is a conjecture which is still open. It is not the only problem, there are many such problems which are known to be NP hard, for which we do not know whether there exists a polynomial time algorithm exist or not, but it is widely believed again that that does not exist, and we do lot of things depending on that assumption. No, what will be the separation? Right, for dynamic programming you need a separation. For general graphs you cannot do a separation. Yes.
now for the time being we concluded a problem with NP hard. So the problem polynomial status is not known yet. Not known yet. Now assuming that problem is NP hard, then further some reductions are made and other NP hard problems are discovered. Suppose in future somebody found that well no, it has a give some polynomial time.
So, if you can give a polynomial time algorithm for one of the NP hard problems,
all NP hard problems
will be can be solved in polynomial time. That is the idea of reduction.
No, actually, why I am asking this question that finding a prime.
It was not known, the status was not known, it was not proved to be NP hard.
2004, Zayed and Manindra Agarwal,
Yes, they proved that primes is in P.
yeah, they gave an NQ algorithm.
Yes, but that primes is in P they proved, but it was prime whether primes is in P or not, like prime numbers, it was not a NP hard problem. It was known as NP hard intermediate. So let us not go into the details. Maybe after the class during the T we can discuss this. Okay. So this is we are deviating from the topic. So bad news that this is NP hard. No hope for a finding. Most likely there is no hope for find the optimal solution. So what should we do? We just stop doing research? No. One way, there are several ways to tackle the NP hard problems. One of them is the approximation algorithm. Very vaguely speaking, what is the approximation algorithm? Okay, I understand that I will not be able to produce a maximum independent set, but can I give you an algorithm which guarantees to produce a algorithm, produce a output which is some constant fraction of the maximum independent set. For example, what is the size of the maximum independent set? 4. Can you produce a maximum independent set of size 2? If we can, then it will be known as a 2-factor algorithm. That you give me any instance, if opt is say k, my algorithm will produce a output say alpha times opt. Alpha is the approximation factor. I will not be able to produce maximum, but I will produce something which is close to maximum. This is very vaguely speaking, this is the formal definition of an approximation algorithm. So, this is opt is the optimal solution given any instance. This approximation algorithm will produce output which is, I cannot give you opt, maybe for some instance I will be able to give opt, but it will be at least 1 by alpha times opt. Clear? Clear? This is known as approximation algorithm. Are you still with me? Now, let us try to find an approximation algorithm for this problem, that we are given a set of unit disks and we would like to find a maximum independent set of disks among the given set of disks. But again, when we find a difficult problem, what we do? We simplify. Let us simplify. Instead of having any number of disk anywhere, I am assuming that the given disks are inside a strip of height 1. The center lies within a strip of height 1. Previously, it is anywhere in the plane, but now I have a restricted input where all the disks lies within a strip of height 1. Can we solve this problem? Still not sure. Again simplify. I will give you a box of sides where the sides are length 1 and all the centers are inside that box. Can you solve this? I have given you n disks whose centers are inside the box, and I am asking you, can you solve this problem? Can you think? It is a very restricted instance. Okay. Hint. How many disks there can be in the maximum independent set in this case, in this particular case? Can there be 5 disks which are independent? 2, 3, after the class you can debate about it. The point is it is constant. How many subsets of size 2 are there? Order n square. Try all of them. Try all subsets of size 3, subsets of size 2, subsets of size 1 and report the maximum. Are you with me? Try all possible subsets of size, the constant size. Are you with me? Is it okay? If it is not, let me know. If it is okay, can you solve this? All the centers are in a strip of length d, height 1, length d. Can we solve this problem in polynomial time? D is constant. Can we solve this? Set yes, this is I assume that this is f of d. I will try all possible. So, that is n to the power f of d, right, n to the power some f of d, maybe multiplied by n factor or something, but this is a polynomial time because d is constant, f of d is constant. So, this is polynomial time. I am only concerned about whether the algorithm is polynomial time or not. I do not care it is n to the power 30 or n to the power 10 or n to the power 2. F is a number of maximum number of independent disk set possible, size of the maximum independent set possible in a disk of length d. It is something around 2d at max. You can do a chai pe charcha after this class what is the actual number, right. We are happy that this is constant. So, we can solve this problem. So far we have some success. Okay. So, let us go to the original problem that we have a strip of length anything but width or height 1, and there are centers lies within this strip. I want to solve, I want to find the maximum independent set or approximately a maximum independent set for this input instance. Are you with me? I need some concentration from you for the next 2 slides. Okay. So, this is a long strip. What I am doing is that I am considering the one length 1 height 1 line segments, that is the part of the line x equals to I, where I is a integer. I can do that, right. I will just divide in. I am drawing this things and I am dividing this set of line segments into 3 classes. One is red, blue and green. What is red? So, suppose this is x equals to 0, this is x equals to 1, this is x equals to 2, x equals to 3, x equals to 4, x equals to 5, x equals to 6, x equal to 7 and x equals to 8. Just I am doing a modulo division operation, I am taking the remainder, if depending on whether the remainder is 0, 1 or 2, I am placing this line segment in one of these classes. If the remainder is 0, I am calling it red, if it is 1, I am calling it blue, if it is 2, calling it green. Okay. This is a long strip, I am just drawn a sample of it. I can do that, right, very good. Now, among the disks given to me, some of the disk I am assuming that some of the disk will intersect a red line, some of the disk will intersect a green line, some of the disk will intersect a blue line. I am assuming that no disk intersect both the lines, or I can shift this whole grid little bit, right. So, depending on the colors of the lines, I can divide the disk also in 3 parts. What are the red disks? Are the disks which intersect the red lines, similarly blue disk and green disk. Now, the funny thing happens. Suppose from the given set of disks, I delete all the disks which are red, I just delete. Now, I have the rest of the disks. Question is, can I find the maximum independent set for this set of disks? I deleted all the disks which intersect the red lines. Now I have some remaining set of disks and I am looking for a maximum independent set for this set of disks. Is it
Every region there can be a maximum of 2 circles.
The whole problem is now divided into 3 disjoint problems and they are independent. I want a maximum independent set here, maximum independent set here and a maximum independent set here, and they have nothing to do with each other. Here in the example there are 3, there can be more, but I do not care, and each of them I can solve it in polynomial time. Okay. And what I am denoting this as MIS 0. Deleting the red disks, finding a maximum independent set, the solution is MIS 0. Similarly, I can find out MIS 1 and MIS 2. What is MIS 1? I will delete all blue disks, find the maximum independent set. What is MIS 2? Deleting all green disks and finding the maximum independent set. And my algorithm is very simple. I will report one of maximum of these 3 sets. That is my algorithm, and see why this is a approximation algorithm. Now forget about what I have done till now. Consider any optimal solution. This orange disk are optimal solution, optimal set of maximum independent set. Like the previous case, I can divide this orange disk into 3 classes again. Right. So, I have from that opt 0, opt 1, opt 2. If you understood till now, can you let me know what is opt minus opt 0? Opt is a set of disks. I have deleted from them the disk which intersect the red disks. What remains is, what is that? What is opt? Opt is an independent set. So, opt minus opt 0 is also an independent set, but this is an independent set for which problem? D minus D 0. This is an independent set for D minus D 0. What is MIS 0? It is a maximum independent set for D minus D 0. So, what is the relation between MIS 0 and opt 0? MIS 0 and opt minus opt 0? MIS opt minus opt 0 is one independent set. This is a maximum independent set, hence this is bigger than this. Similarly holds for the other 2 cases as well. Still with me? Looks confused.
What is MIS 0 is equal to, say,
MIS 0 equals to opt minus opt 0, greater than equals to. This is greater than, not greater than equals to. This is one independent set, opt minus opt 0 is one independent set, maybe it is a maximum, may not be, but it certainly is great. MIS 0 is certainly is greater than opt minus opt, because this is maximum independent set. Okay. Now some, okay. What is MIS 0? You will tell me. Independent set in D minus D 0. What is opt 0? No, it is an independent set, D minus D 0. opt is a maximum independent set of the original problem. From them I am deleted the disk which intersect the red lines. What remains is still an independent set and belongs to d minus d0, but there is no guarantee that this is a maximum independent set for d minus d0, but certainly it is an independent set, right. So, I know that the maximum independent set for a problem has to be greater than the kernel has to be greater than the any independent set, right. So, similarly for the blue and similarly for the green. Now, some trivial pigeonhole principle. I know that one of the opt 0, opt 1 and opt 2 is at most opt by 3. Right, one of them has to be simple pigeonhole principle. Then we have what we have. We have started with MIS 0. Suppose this is opt 0 is less than equals to opt by 3. What we know? MIS 0 is greater than opt minus opt 0 from here, right, and opt 0 is at most 1/3 of the opt. So, MIS 0 is at least 2/3 of the optimal solution. So, what we have done? We have reported the maximum of MIS 0, MIS 1 and MIS 2, that is also has to be greater than 2/3 of the opt, right. Are you with me? Have the idea? Okay. How much time it will take to find this solution? N cube for each strip, right. So, roughly speaking it will take n cube time. So, there is a this is not right to find the optimal set of size right. This is our algorithm. So, deleting 1/3 of them, right, and in time vaguely n cube. I am finding a solution of size opt into 1 minus 1/3. How many divisions we have made? 3. Why? Why 3? What happens for any value epsilon between 0 and 1? I can make 1 by epsilon many divisions. I can use 1 by epsilon many colors. Why 3 colors? I can use 4 colors. Then the complexity will be n to the power 4, because the each problem will be of size n to the power 4. I can use 5 colors. Then complexity of each problem will be n to the power 5. I can choose 5 independent disks from each of them. I can choose 6, 7, 8. Complexity will increase, but what is the approximation that we will get? I will go close to the optimal solution. The more complexity I will put in, I will keep going more towards the optimal solution. So, this is kind of a general approximation scheme. You tell me how close you want to go, I will give you an algorithm, but you have to pay in the complexity of the algorithm. So, in time n to the power 1 by epsilon, I can produce by the same scheme, if you think about this, can produce a solution with a guarantee of size 1 minus epsilon into opt. This is called a p-toss or a polynomial time approximation scheme. This is one of the best kind of approximation that you can generate. There is no bound. It is not saying that I will give you 2 approximation, 3 approximation, 4 approximation. You tell me what approximation you want. But depending on that, how close you want to go to the opt, you have to spend that amount of time for the runtime of the algorithm. It is a generic scheme.
For clique problem, for general graph clique problem, so we have that we have some application of that.
Yes.
Vertex cover using vertex cover, right? So for that, can one divide it as a kind of algorithm?
Okay. So, this is approximation. There is something called a hardness of approximation. You can prove that if you can, for some problems you can prove that, for example, if for independent set you can prove that if you have a p-task, then you can solve a NP-hard problem in polynomial time. This is called a hardness of, you cannot even produce a p-task for general independent set for general graph classes. Yeah. Now you have to see for different problems what you can do, what you cannot. That is why I was saying that independent set is a notoriously difficult NP-hard problem. Forget about p-task. Give me a constant factor. Cannot even give that. So there are different. I will not go into that details. There are different classes of approximation algorithm. Their hardness. This is just a overview and one such possibilities. Okay. Thank you.